All right, welcome back. Today's Tuesday, May 12th. We're going to continue on kinetic energy. I know a lot of you love football, and it's too bad that right now all the sports are kind of stopped and stuff like that. But let's imagine you were drafting an NFL defensive end. What are some of the things that you would look for in a good football player? Well, one of the things is probably mass, right? You probably want a pretty big football player, pretty muscular. You don't want a little toddler over here. Another thing is you want speed. You want someone who has a lot of speed, and when you add those two together, mass and speed, you have a lot of kinetic energy, and so you want to find a defensive end that can generate a lot of kinetic energy really quickly, so you can sack the quarterback. So this is on page 87. You're going to take notes on PS3-1, kinetic energy. So kinetic energy is all about the energy of motion. So the more something moves, the more energy it has. And so there's an equation that helps describe this, and its kinetic energy is equal to 1/2 mv squared. And through this equation, you can see that the amount of kinetic energy depends on two things. It depends on how fast something is going, and it depends on how much mass it is. So the more mass it has, the more energy it has. Makes a lot of sense. A softball has more mass than a ping pong ball. Now the speed has an even bigger effect. The faster something is, the more energy it gets squared. So just by doubling the speed, you get 4 times the amount of energy. So that's why something like a bullet will have a lot of kinetic energy, because even though the mass is small, the velocity is super high. So here's some more examples. We have a bullet that's going to be shooting through an apple, so a lot of kinetic energy there. A pitcher, the faster you throw the baseball, the more energy it's going to have. A bowling ball, the more massive your bowling ball is, the more energy it's going to have. And if you have a whip, believe it or not, because the end of the whip is so small in mass, it actually goes a lot faster because all that energy is conserved, and so that's why you get that snap. And so I have a quick video about the whip.
At first, when you crack a whip, all of the momentum is spread out across the entire whip. But as time goes by, that same momentum, or roughly the same momentum, is on a smaller and smaller portion of that whip. In addition to this, most whips have mass tapering. At the very end, it's very heavy, where at the front, it's very light. This means that the same amount of momentum, or roughly the same amount of momentum, is on a smaller mass. And since momentum is a mixture of velocity and mass, as the mass decreases, that means that the velocity will increase. That means that when the momentum gets to the very tip of the whip, it'll be going extremely fast, faster than the speed of sound.
So in all of these cases, it's all about the mass and the velocity. The more mass something has, the more kinetic energy it's going to have. The more velocity it has, the faster it goes, the more kinetic energy it's going to have. And the kinetic energy is the energy of motion. Okay, see you tomorrow.